So in this example, this worksheet, we're going to look at solubility products specifically. Um, a solubility product is an equilibrium where the reactant side of the equation is a sparingly soluble or insoluble salt. Um, in this particular example, we're going to start off talking about calcium fluoride. So calcium fluoride is a solid um, in equations. And because it's asking me for molar solubility, it's giving me a very, very small amount, 1.24 millimoles per liter. So we're going to write this out as an equilibrium, where the product side has aqueous ions, which would be the dissolving or dissociation, and the reactant side has solids. So what I want to do is I want to determine the KSP value for this. So KSP, which is just a Kc, is equal to the reactants and products ratio. Now, of course, with solubility products, because the reactant is solid, we don't write anything on the bottom, or the whole expression is just over 1. With the molar solubility, what we are saying is we're saying that 1 mole of this will dissociate into that many moles of the ion. So that would be that many moles of calcium, but double that for fluoride because it's a 2-to-1 ratio. So I know I don't have what this is, and it's a solid, so it's not going to factor in at all with our problem. So this tells me I have 1.24 times 10 to the negative 3 moles per liter of calcium, and that tells me I have 2.48 times 10 to the negative 3 moles per liter of the fluoride. So when I am asked to determine the molar solubility, I am basically looking for trying to solve for one of the ions on the right-hand side of the equation that has the same stoichiometric coefficient as our reactant. So now we solve 1.24 times 10 negative 3, 2.48 times 10 to the negative 3, and we have to square it. So 2.48 exponent 3 negative squared times 1.24, and I get a KSP value equal to 7.626 times 10 to the negative 9. With significant figures, it's just 7.63. And that's all we're doing. The one thing we have to look out for is make sure that you are doubling this value when the coefficient is 2-to-1. What I sometimes see is that people are just putting this number in and assuming that the square is taking care of that, and they're not really connected in that way, so you have to make sure that you double it. So for question 2, it says the KSP of lead carbonate is 7.4 times 10 to the negative 4. What is the concentration of lead plus 2 and carbonate in the saturated solution of this compound? So we write lead carbonate solid is dissociating into its ions. It's telling me it's a KSP problem right off the bat, so I know what I'm going to do. So we look at our KSP is equal to lead and CO3 negative 2. I have no idea how much of this is produced. So KSP is equal to X times X is equal to X squared. So 7.4 times 10 to the negative 14 is equal to X squared. We just solve for x. (2.72) times 10 to the negative 7 is equal to x, which is equal to the concentration of lead plus 2 and carbonate minus 2. And that's all we do for that particular problem. Very nice and easy when the ratios are the same. It gets a little bit more complicated, a little more annoying as you add greater numbers of ions. So the next part of the question says, if 20 mils of 0.25 molar lead nitrate is added to 30 mils of a saturated lead carbonate solution, what will the concentrations of lead and carbonate be given the above KSP? So PbCO3 solid So now we have added a common ion, lead carbonate. Lead carbonate is basically producing this amount of lead and carbonate. So initial we are started with 0.020 liters times 0.25 moles per liter of the lead nitrate. So we have to figure out how many moles are being added. So it's 0.05 moles of lead plus 2. What we're looking for is we're adding lead nitrate. All nitrates are soluble. So what you're really looking for here is what are the ions. So lead nitrate will break into lead ion plus nitrate ion. I go to my equilibrium here and I see that I have lead carbonate. So in this particular example, to get the concentration of the lead ion, I take the number of moles I just solved and I divide it by the total volume. So 20 mils plus 30 mils is 50 mils of solution. So the concentration of lead plus 2 is equal to 1 mole per liter. So I'm going to go up and put in this. So we're assuming that no carbonate is actually associated yet. We're assuming that we have the lead nitrate in solution, or 1 mole per liter lead plus 2 in solution. We know that this is going to dissociate, producing X and X. So I get 1 plus X in the equilibrium line and X. We're now going to use exactly what we've done before. So we have our KSP expression. KSP is equal to the concentration of lead plus 2 times the concentration of carbonate. Now we can do our test here just to see that if we can ignore X. So 1 mole per liter divided by 7.4 exponent 14 negative is 1.35 times 10 to the 13. That's a lot bigger than 500, so we know that we can ignore any gain of X to the lead ion concentration. So we know KSP is equal to 7.4 times 10 to the negative 14. We know the concentration of lead is 1 mole per liter. What would the concentration of carbonate be? I'm going to divide both sides by 1. X is going to be 7.4 times 10 to the negative 14. So we can solve our solution. So our solution has 1 mole per liter of lead plus 2. Our solution will have very, very little carbonate, and you can see how much the carbonate has dropped, and that's exactly what Le Chatelier has predicted. As we stress this side by adding lead, it will force equilibrium to the left. In other words, it will make this less soluble. Less of this will actually dissociate. Finally, what we're looking at for part C, it says, will the addition of HCl increase or decrease the solubility of lead carbonate? So we have our equation again. We have our equation. This was in our lab. We know that if we add acid to a compound containing a carbonate, which is the conjugate base of carbonic acid, it will react to form CO2 plus H2O, basically removing this out of the reaction, forcing this equilibrium to the right. So the question is, will the addition of HCl increase or decrease the solubility of lead carbonate? It will increase, because CO3 minus 2 forms CO2 plus H2O. Unstressing products to increase solubility. So remember, you have to identify if the acid is going to react with this particular compound. Normally, it's obviously not going to be the cation because the cation is usually acidic.